Okay, let's continue. The last course for today is given by Alec Jacobson, and Alec Jacobson will soon start as an assistant professor in Toronto. Right now he's a postdoc at Columbia with Eitan Grinspun, and he did his PhD was working at ETH Zurich. And one line of his research is addressing interactive shape deformation, and today he will give a course on skinning and real-time shape deformation.
Thank you very much, Klaus, and I'd like to thank Eitan and Klaus for inviting me to come and do this course today. So the topic of this course is skinning, and especially for an audience that might contain people not necessarily in computer graphics exclusively, I should define what I mean by skinning. So in animation, ultimately, we only really render the character's skin, or their clothing, or their outer appearance. So traditionally, skinning is the process of moving the high-resolution skin geometry of a character, the outer geometry of the character, the surface, with a low-order skeleton inside of the character. So we have a human character, we might have a few bones inside of the character, and those bones are being moved around by an artist, and that the transformations that are being applied to the bones should then propagate to the skin, to the surface geometry. In this talk, and in general in the literature these days, we'll loosely define skinning to be any real-time deformation system that's controlled by a small set of intuitive parameters. And the important bits here are the focus on things that are real-time, so you get immediate feedback when you change the parameters. And the parameters are somehow can be understood by an artist or a user. So if you change the value, if you twist the knob, the user should already have some expectation of how that's going to change the deformation. So this course was originally presented a couple years ago at SIGGRAPH, and I'd like to acknowledge the other people that helped me craft this course. So this is me. I have less hair today, and I'll be at University of Toronto in the future. But the rest of the course was designed by Zhigang Deng at University of Houston, Ladislav Kavin, who's now at University of Utah, and J.P. Lewis, who's at Victoria University in Weta Digital. So I'm really humbled to be with the rest of these authors because they're really leading experts in this field. Today, it's a shorter amount of time, so I can't present the entire SIGGRAPH course. And I'll present the parts that correspond to Ladislav's part, which will be the first part that I'll talk about, the direct methods for skinning, and then my part on automatic methods for skinning. So I'd like to quickly overview what this course will cover. So I'll talk about popular basic methods for real-time deformation. We'll try to cover things that are approaching the state of the art. This slides are going to miss out on maybe the papers that you'll see this year at SIGGRAPH, but we're really getting close to the state of the art in this talk. And I'd like to give you a little bit of an academic and an industry perspective on how these tools are used. And finally, I'll hopefully leave you with some ideas of what you can take back to your labs for open research questions. So we have notes online, and you can think of the notes for each of the sections that we work on as a sort of detailed survey that contain plenty of references for all the methods that are covered here and beyond. There will be deeper mathematical comparisons and derivations of the topics. I'll be giving an abbreviated version of Ladislav's direct method, so there's more on that online, and the slides for that are online. Zhigang Deng presented some work on the survey and course material on mesh animation decomposition via skinning, so looking at animations and trying to reverse them and understand them as a real-time shape deformation process. And J.P. Lewis talked about example-based or data-driven methods for skinning. So finally, it pays to talk about what this course won't be covering. So we won't be talking about real-time physically-based simulations, where you set up some physical laws of motion and push go. So that won't be covered here. We won't be talking about techniques that are specialized to very specific types of geometry, like faces or hands. And this is not a course on how to use Maya or Blender. And then as a side note, we'll dip into this topic that's very popular, especially within the geometry community, called generalized barycentric coordinates. But this shouldn't really be seen as a survey or a course exclusively about that, because you could wax and wane about that topic for much longer than I will. Right, so I had times up here before, but I just deleted them because we started a little bit late. But I'm going to try to talk about direct methods for 15-20 minutes and then talk about automatic methods for the rest of the hour. And so you'll see this URL coming up a couple times throughout the talk. So skinning.org is where we put all the notes, slides, and other material for this talk. Specifically, the parts corresponding to what I'm talking about, and also Zhigang and Jake Lewis's parts. Switch over here. So as I defined in the beginning, skinning is really broad. We can say it's any real-time deformation system controlled by an intuitive set of parameters. But we can separate these broadly into two classes: the variational or energy optimization methods and the direct methods. So a variational scheme will be similar to some things that we saw this morning in the fields of parameterization, where we say that the new positions of every vertex of the geometry, this V prime here, should be the result of some energy optimization. And that energy optimization might take the user's input as parameters, and it might chew on them and run some sparse linear system solvers or gradient descent and so on, and then finally spit out the deformation of the surface. In contrast, a direct method should represent the output geometry at every frame as a closed form expression of the input parameters. So it's just some equation that we can evaluate. And the most popular form of this, and you'll see this equation really showing up a lot in this talk, is linear blend skinning. So in particular, you have a sum over a set of handles. These you can think of for now as the bones inside of your shape. And each of these defines a transformation, T, and that's being applied to the rest vertex of the geometry. So we're taking a weighted average of these transformations applied to the rest geometry, and that spits out our output vertices V prime. So here's a little visualization of that setup. So linear blend skinning, we have the rest pose, so that's your vertex there on the mesh. You have your bones inside of the mesh. So this is still in the rest pose on the left, and now you have a posed position of that arm. So we have some transformation that takes the forearm to its new position and takes the upper arm to its new position. For each of these bones in the skeleton, you have corresponding skinning weights. You can think of these as functions that live on the surface and tell every vertex how much does it belong to each of the bones in the skeleton. So in places where it's bright red here, it's fully attached, 100% attached to that particular bone. And then it's fading off to 0% where it's no longer attached. So you have these regions in the middle, like the elbow, that are sort of attached to both of them. You get a blend of the transformations happening to both bones. And linear blend skinning can be understood in two unique ways. It's the same equation, we can understand it in two different ways. So in the left version of this equation, we can think of it as each bone applies its transformation to the entire shape. So for every bone, you have sort of its view of what's happening to the shape. And then the weights, the weighted averaging, is just spatially varying a weighted average of those entirely blended bodies. So if I have my arm moving like this, the arm might see my entire body moving like that, but the weights control the blending so that I get a nicely blended arm. In the other view, you can see it as the weights being applied to the transformations. So every vertex is getting transformed by a weighted blend of transformation matrices. So linear blend skinning and in general other direct methods are convenient compared to the variational methods because we can run them directly inside of shaders. So if you're familiar with the real-time graphics pipeline, you send your triangle mesh to the shaders that run on your GPU, and then in parallel, all the vertices are being processed by the shader. And in particular, with deformation methods, those vertices can be moved. And if the deformation method is direct, if it's just evaluating some equations, then the shader can just say, okay, I know what my weights are at this vertex, I know what the bone transformations are, so move me to my new skin position. And for this reason, linear blend skinning is enormously used in industry. So it's used in basically any video game that you can find, including the sort of AAA games like the Halo games. It's used in film production too as a first step for deforming characters. But despite this amazing popularity, linear blend skinning has really well-known artifacts. We know that this equation can break down in kind of dramatic ways. So consider this, for example. So we have one bone, two bones, sorry, controlling this brick shape. So imagine this guy's arm is a brick. If I apply a twist to his arm. Oh, sorry, thank you. So we have this guy here. Whoop, no, I'm over here. So if I apply a twist, thank you, let's go. Here, you can see that the elbow is completely collapsing. So it's losing all of its volume in the elbow. Let's switch back to the talk. The reason for this is if we take that view that we're blending the transformations, so we have one transformation matrix that's turning by 180 degrees, and we have another one that's an identity. We view those as matrices. What's going to happen when we take one half of one of them and one half of the other one? I'll use this as a mild attempt at our audience participation. So we have identity times one half plus one half times a rotation by 180 degrees. What will the resulting transformation matrix be? It will be a rotation. Let's try it on the board. Okay. So that's our identity, right? And we have a so do we agree that this is a rotation by 180? Okay, good. I didn't mess anything up that badly. So what do we get in the first part? Oh, this isn't what I want. This is 90 right now. That's what I wanted. Now it should be group of geometers, we should be able to figure out a rotation by 180. All right, so I'll cut to the chase here. So you get something like this. And now we can see in this part here that we get this collapse, right? Anything that lives in this space is just being collapsed to zero. So that's exactly corresponding to the joint collapse, this candy wrapper artifact that we see when we're twisting this thing, all the volumes being lost in the center. So a variety of different methods have been invented to counteract this kind of volume loss that happens uniquely because of the simple linearity of linear blend skinning. So I'll talk about two different methods in this talk for attacking this problem, the simple problem of linear blend skinning. So one of them we'll call the multilinear methods, and these methods will work by introducing new parameters, not just skinning weights, but more weights into the problem. So they're in some sense linear in a larger space. And then there are methods that are nonlinear, so still closed form, but now the blending that you're doing is in a nonlinear space rather than linear. And there are advanced deformation primitives that solve this in a different way, but I won't cover those right now. So these are the references for the multilinear skinning techniques. And both of these methods will introduce new weights for each of the bones. So you don't just have a single scalar field. At every vertex, you have a collection of weights that then control how that bone's transformation gets propagated to the shape. So let's back up a little bit. We saw the summation form of linear blend skinning. But in general, we can view linear blend skinning, or any sort of linear operation, as a matrix multiplication. So if we take our transformations and just stack them into a giant vector of degrees of freedom. So we have our transformation matrices. They're affine transformations. For each bone, we have a 3x4 matrix, so 12 degrees of freedom. We have m bones. So we have a big vector of parameters that's 12m long. And then the weights and the rest positions get collected into x. And for now, let's forget about what exactly x is. But the important thing is to note that x is representing the linear deformation spanned by these parameters that we have for the bones. So x will aggregate the rest pose information, where the vertices started from, and what the weights are. And then this spits out the new deformed vertex positions. So we get a deformation like that. So x has a certain structure. It has a block structure, and each of the blocks corresponds to the bones, the weight applied for each bone for each of its elements in its 3x4 transformation matrix. So we can see exactly how that parameter is being applied to the shape. And in particular, linear blend skinning, if we just have a single scalar function for each of the bones, then we see that this block structure continues even farther. For each of the blocks, we see that the weight is being applied to just an identity matrix for each of the x, y, z, and the translation component of the transformation. So if we write this out, if we explode this into the matrix form, then for each bone we see something like this. So we see that the same weight, Wij, is being applied to all parts of the rest pose. So there's just one weight per vertex per bone. And the concept of multi-weight enveloping was to say, hey, there's an opportunity here for us to provide more parameters to control this plate. Why should the transformation see the same weight for every part? We should be spanning, we have the potential here to span a larger space. So in particular, what multi-weight envelope is doing is saying for each of these values, stick in a new weighting function. So now you have actually 12 weights, 12 scalar functions per bone. And this is much more powerful. And in particular, you can get rid of this candy wrapper effect that's happening near the shoulder. So here's the best possible deformation that you can make using linear blend skinning. But if you expand this space and you allow more weights for each bone, you can reduce this volume loss. One of the problems with multi-weight enveloping is that there's no intuitive understanding for how this particular part of the transformation matrix should be controlled. Like, what should the weight be for how the y component of the deformed vertex responds to the x component of the rest pose? This is somehow not an intuitive parameter to come up with. So as where linear blend skinning weights, you can really see them as a function on the surface that could be painted. You can imagine an artist, and indeed they do, paint these functions on the surface. The multi-weight enveloping weights need to be trained from example poses, which is a bit of a chicken and egg problem, because you're trying to come up with a scheme for deforming a mesh, and yet now you need example poses to define the scheme that then you would like to use to deform the mesh. Animation space makes an interesting observation on top of multi-weight enveloping, that multi-weight enveloping is in some sense too general. You've actually added too many degrees of freedom if we want the deformations that we're controlling to be rotation invariant. So rotation invariance means that if we if we apply a transformation in the rest pose, or we apply those same transformations but rotated by a global rotation, we'd expect to get the same deformation, just rotated. It's a very natural thing to do. If we have a character that's turning around, we'd like his arms to behave in the same way as if he did those operations in his rest pose, and then we rotated him afterward. So to ensure rotation-invariant linear blend skinning, and I invite you to look at Ladislav's course notes online, you can prove that the only weight that you're allowed to choose now is to have a different weighting function for sort of each column of the transformation matrix. So you can have a separate scalar weighting function for how the deformations depend on the x, y, z, and then the homogeneous component. But you're not allowed to use the full 12 degrees of freedom of multi-weight enveloping if you want to guarantee multi-weight rotation invariance. So you have then 4 weights per vertex per bone. Translation invariance is somehow a simpler condition. So for linear blend skinning, translation invariance you get so long as your weights sum up to 1. And in the case of animation space, we just need that those last weights add up to 1, the ones that control the translation, the homogeneous part. So if we take this exploded view here, remember in linear blend skinning, we have the same weight going across all of these diagonals. In animation space, we see that we have one weight controlling the first 3, a second weight controlling the next 3, and so on. So we have 4 weights controlling this, the effect of this transformation. So similar to multi-weight enveloping, we can get rid of these artifacts like the candy wrapper effect. But again, we have this problem that these weights, how each vertex corresponds to the different components of the rest position are somehow unintuitive, need to be trained from examples. So in summary, the idea of the multi-weight, the multilinear methods are trying to improve the quality of the real-time deformations that we can get by introducing more parameters, by introducing more weights. One thing that I might not have said at the very beginning is that these weights are fixed. So when we set up the deformation system, the weights are fixed, they're set in stone, and the only thing that the user is controlling at runtime, as we see in new frame the animation, is the transformations of the bone. So that's an important takeaway here, is that the weights are something that we pre-compute, and then you deform the shape later. So now I'd like to briefly touch on nonlinear methods. So if we go back to that linear blend skinning formula, and we look in particular at this right view, we see linear blend skinning as taking a weighted combination of transformations and then applying that to the rest position of the mesh. We can see that, as we noted on the board, one of the problems here is that we're blending rigid deformations, rotations, as matrices, and we might not get out a rotation matrix, right? The problem is that this really isn't a rotation. And even if we weren't blending 1/2 by 1/2, any values that aren't just 1 and 0 will get some amount of scaling happening in that upper corner. And that's because a weighted combination of rotation matrices is in general not another rotation matrix. So what we'd like to be able to do is have some direct closed form expression for combining rotation matrices such that we always get out a rotation matrix. And to do this, let's look back to the spaces that we're actually working in. So if we think of the rotation matrices as the special Euclidean group in 3D, you can have sort of a corny visualization of what this space looks like. So this is, just imagine this as some oval, and we have 2 transformations that exist on this manifold. If we take some weighted blend, we end up somewhere in between. So we're decidedly not lying on the manifold. We know we don't get rotation matrix when we take a linear combination. And it's really bad if we're taking a combination of things that are across from each other. So in some sense, these two are across from the center here, the singularity point. And there we know we get into a lot of trouble in terms of the volume loss. And here's exactly that same situation. So we took a 1/2 blend of these two. We know that we get a singular matrix. So what we'd like to be able to do is take some intrinsic blend. So define some blending of these matrices such that we actually stay on this manifold. And then we get something like this. So one solution that was presented for this kind of blending was to look toward an alternative representation of rigid transformations in 3D. And in the literature, you can find a concept called dual quaternions, and their averages will be an approximation of this intrinsic average of the special Euclidean group. So the important thing to note is that any rigid transformation matrix can be converted into a unit dual quaternion. So this is a quaternion that will have, you can think of it as two quaternions tied together. So here we don't have an animation, I bet. That's really lame. Oh.
We can see it up there.
Oh, you can? It did?
Yeah.
Did the other one go?
Yeah.
Ah! I'm like looking and I only see, it's not going. Do I have to like look down? Oh, that is not fair. It's showing me nothing down there. All right, so what you're seeing is just a rotation being applied to this teapot. And this is the first four coordinates of a quaternion. And now you're seeing a translation, and you're seeing the coordinates of a dual quaternion. So a dual quaternion is a quaternion that has a dual number as its coefficients rather than a real number. So the translations control the sort of dual coefficients, and if you combine these together, you get rigid transformations that will light up both the scalar part and the dual part of the dual quaternion. Okay. So you can ask yourself, if we know that every rigid transformation matrix can be converted into a dual quaternion, is there a one-to-one correspondence between these rigid transformation matrices and the space of unit dual quaternions? And the answer, surprisingly and actually luckily, is no. A unit dual quaternion and minus that dual quaternion actually represent the same transformation. So in this sense, the space, or the manifold of unit dual quaternions, is a double covering of the space of rigid transformation matrices. And we're going to exploit this to get a better real-time shape deformation, a direct method. So if we look back at that picture where we had sort of the worst-case scenario of blending two rigid transformation matrices, we could get something that goes through the center, so it hits that singularity point. But since we're working with a dual covering of this space, we know that any 2 points are half as far away in some sense on this manifold. So if we take the corresponding unit dual quaternions, we get something like this. And now if we cut through this space, even if we take an equal average of these dual quaternions, we know we're away from that singularity point. So in this sense, the space of unit dual quaternions is less curved, let's say, than the rigid matrices. And to do that, so we can exploit this to get a fast closed form projection back onto the space of unit dual quaternions. So we can simply take the average of the coefficients of this of two unit dual quaternions, we get something in the middle, and then we'd like to be back on that space, so we simply normalize this. We normalize this to be unit norm. And this is a direct operation, so it's just a weighted blend of coefficients and then a normalization, so a little division. Are these sliding? Ah, that's so unfair. Okay, so here you're seeing that candy wrapper artifacts where we're blending, and dual quaternion sort of does the natural thing, so it's twisting the box without any sort of volume loss. So dual quaternions are really only working with rigid transformations. In some cases, it's nice to work with the entire space of affine transformations. In particular, you can use this for a sort of crude muscle bulging effect. So we might control this woman's arm and have sort of her muscles bulge out when she flexes. And to do this, at least for now, you can apply some scaling first and then apply the dual quaternion rotation. And this sort of effect was actually enhanced in production and used by Disney for one of their latest Frozen movies. So this sort of thing is actually used in practice. So Maya and Blender, they both have implementations of dual quaternion skinning in addition to linear blend skinning. Lastly, I'll leave you with some sort of trending topics in direct methods. There's an interesting series of work by Valiant and colleagues in France that are introducing contact handling and response in the direct skinning framework. So, and in this example that you see on the left here, you have a linear blend skinning deformation of a finger, and if we're just moving vertices according to averages of weights, there's no way that the tip of the finger is going to respond with the palm of the hand. You don't get sort of that nice cushiony effect that you see with your happening at your knuckles or your finger against itself. But they use some interesting insights and pre-computation to be able to handle things that look like they're approaching these contact effects, but do it in real time with the direct method. So I invite you to look at those works. I'll remind you again, the course notes for this part are online. And if we want, we can take questions regarding the direct methods now. There haven't been many questions all day. Does anyone have a burning question? It's going to eat them alive during the automatic part.
So how do you compute the weights?
Ah, that's great, because that's what the second part is going to be about. And if you really just bear with me 1 second, I'm going to switch the display because I have a couple more demos and I want to actually be able to see them. Okay. I think that'll work. All right, so automatic skinning method. So I will talk in this part about how do we come up with these things? Where did that skeleton come from? Where did these weights come from? We assume that we might have some artist that's willing to move around these bones and apply transformations. You might use dual quaternion skinning or linear blend skinning, but it seems like there was a whole lot of parameters and setup involved in creating the linear blend skinning rig, as they call it in the industry. And indeed that's true. So the traditional skinning pipeline, if you will, is very labor intensive. So the first part is designing your character and loading in your model, and then coming up with some set of handles. These are going to be the parts that you're applying transformations to control that shape. So in this example, you can see the blue skeleton inside. So these are a skeleton made up of rigid bones. In other deformation settings, you might just have points, loose points that you selected on the character. You can see the yellow dots here. That those will be the handles. In different scenarios, you might be controlling a surface deformation. You just want to select entire regions of the surface. So these will act as the handle sets. And then in the realm of generalized barycentric coordinates, and in particular for controlling sort of volumetric deformations, we can think of a coarse polygon or polyhedron surrounding our object as a cage, and applying new transformations to the cage vertices. We'd like those to be propagated in the interior in a direct way. So the cage itself becomes the handle set. So someone needs to come up, someone or something needs to come up with this handle set. And once we have the handle set, we need to paint these weighting functions. So traditionally, in a production studio, there will be a person who's hired really simply to paint these weighting functions for every character and set up these rigs. Paint them, normalize them so that they sum up to one, try the deformations, they see some error, they zoom in, they repaint them. Maybe the modeler says, oh, I'm going to change the shape a little bit, then they think, I have to go and repaint those weights. Once those weights are finally set, only then finally can a different artist usually start transforming the character by applying transformations to each bone. So if we want to control this entire armadillo character, we'd have to apply 17 different transformations, so 17 times potentially 12 degrees of freedom that now need to be controlled by some graphical user interface or some table of numbers. So the concept of this part of the course is to acknowledge that recent research can actually automate or help assist each of these processes. So we can help construct handle sets automatically, we can compute the weights automatically, we can even help the user choose these transformations to reduce the effort and tedium of the process. So I'm going to very briefly talk about how do we come up with the handle sets in an automatic way. This seems like a very ill-posed problem. What we know from our anatomy and the anatomy of most of the creatures around the world, that the skeleton of that character or that animal controls the shape, or it somehow implies the shape. At least the low frequency deformations of this dog are really controlled by where his bones are. So indeed, in classic illustration textbooks, where they're teaching students how to draw characters, they'll say, first draw the skeleton, get the skeleton in the right place, and the rest of the shape is somehow implied. You can sort of just fill in where the belly should go after drawing where the bones go. Well, the concept that we'll exploit to construct the skeleton automatically sort of flips this on its head. From the geometry, can we determine what is sort of the core skeleton inside of the shape? So does the shape imply the skeleton that's making up, that would be responsible for controlling this as if it were an anatomical actor? We can break apart the state-of-the-art skeleton extraction techniques into sort of two camps of research. Some of those are potentially of a lot of interest to the geometry processing community that are based on geometric flows. So taking a surface and trying to flow it and smooth it until it's now changed from a two-dimensional closed surface to a one-dimensional sort of graph of curves, which we can then interpret as a collection of rigid bones. And the other camp is looking at segments of the shape and trying to identify which are the parts of the shape that should be deforming rigidly. Like if you could look at my body, you could say, well, this part really belongs to one rigid piece. Then you can determine that there should just be a single bone controlling that part. I ironically pointed to the one part that has two bones, but you can give me artistic license. So here's an example of a surface flow degenerating a skeleton into, or degenerating a surface into a one-dimensional graph. And what I love about this line of research is it's actually exploiting a fact that was really annoying from the mesh smoothing point of view. If you were trying to smooth this dinosaur, the fact that mesh smoothing creates these sort of one-dimensional spikes and little features was kind of a frustrating aspect of smoothing. But here they're saying, no, this actually tells us something interesting about the geometry here. So really all we're doing in this example is running run-of-the-mill Laplacian smoothing and identifying whenever it becomes degenerate, just freeze it as if it's a one-dimensional part, because we know it becomes degenerate when it loses all of its area. And there's even more recent works that can show that you can sort of guide this thing to actually lie on the medial axis, which is a nice feature if you want your skeleton to be inside of your shape. The other set of works are trying to identify these rigid regions that I mentioned before, and then coming up with a graph of segments that would control these rigid regions. But how would you know ahead of time which parts should deform rigidly if you don't know anything about the shape? You don't even know that it's a cow or that it's a human being. Well, one way, we looked at as rigid as possible energies a lot this morning, is to look at eigenmodes or vibration modes of the as rigid as possible energy, which sort of tell us which parts of the shape should move together. If we look at the low frequency modes, so we're seeing, is it playing just as choppy for you as it's playing for me? Yeah. Well, that's disappointing. So you see that the legs are moving together. You see each leg, you're not seeing some wild oscillation in the high frequency of the legs. We're identifying automatically the rigid parts of this cow, which then we can turn into a segmentation and finally into a graph. There are plenty of open problems in terms of skeleton extraction. In one sense, the joint placement is not really being considered by any of these methods. Where exactly that joint should be, which has a huge impact in sort of the quality of the deformation near the joint. And then guaranteeing that the bones, especially if you simplify them into straight lines, that they lie inside of the shape is also something that's difficult to incorporate into these frameworks. And so far, none of them are trying to respect any sort of intrinsic or extrinsic symmetries in the shape. And in particular, I think that the missing piece here is that the skeletonization methods aren't necessarily aiming toward creating skeletons for linear blend skinning. There's sort of other reasons we might like these curved skeletons as sort of an abstraction of the shape. But if you took a very focused view on linear blend skinning, you could say, I want to measure the success of my skeleton extraction method insofar as it produces a nice linear blend skinning deformation. That would go a lot farther. Another related problem is to look at skeleton embedding. So assume that you know the topology of the skeleton and maybe even some rough geometric details. So you know you want to take a generic skeleton of a human being that has a certain set of bones and feet on the ground, head on the top, and you want to embed that into your shape by changing the length of each bone and the positioning. And this is in some sense a hopefully simpler problem that can have a more robust solution. And in particular, there's a solution out there that will really just say like, okay, I'm gonna write down all the things that I'd like the skeleton to have. So I don't want the bones to be too short, I don't want them to be too long, I want the feet to go at the bottom, I don't want bones to overlap. And if we can write all of these in terms of some energy or cost function that measures how badly we're not satisfying that constraint, we can throw these into a collective energy that then we can try to minimize subject to where the joints can go. And the trick here then is to figure out, well, how should these energies be weighted with each other? And the solution that was presented back in 2007 was probably unsurprising these days, but was to use machine learning based on a set of examples to determine what should the weights be to produce the best possible examples. Skeleton embedding is also an interesting open problem because those energies that we saw before, similar to what I said about skeleton extraction, they're not measuring the implied deformation if you actually used that skeleton. Another challenging case is dealing with partial skeletons. So suppose I have a skeleton of a hand that I'd like to embed into this shape, or even just a single finger. But there's many places we could put two bones. You know, we could put the two bones on the front leg, on the back leg, on the neck, and the left arm, right arm, and the front thumb. So the partial embedding problem is somehow much more ill-posed than the full skeleton embedding. All right, blazing along. There's also methods for automatically computing cages to control a cage-based deformation of a shape. And here we really get into interesting geometric problems. So most of the generalized barycentric coordinate methods that can create automatic weights for a cage-based deformation require that the cage is strictly outside of the shape. So we need to be sure that any part of our geometry is lying inside of that cage. This is easy to do if we just take a cage that includes everything, but of course if we want some intuitive control for the artist, we want this cage to be tightly fitting to the shape. So these two criteria are sort of at odds with each other. In addition, we want them to maintain the symmetry of the shape, or to be sort of well placed with respect to their effect on the deformation. And there was a recent attempt at least solving the enclosure part of this last year at SIGGRAPH Asia. So let's assume that we have used one of these automatic methods, or we created a skeleton or some control mechanism for our shape. It still remains to paint the weighting functions on our character if we want to deform it. And the weighting functions for linear blend skinning should obey a few basic qualities. If we want a smooth deformation of the shape, the weighting functions themselves must be smooth, since we're taking just a weighted average. For each handle, we expect that weighting function is 100%. It's 1 underneath that handle. And if we want the part of the shape that's controlled by the other handles not to move, then that weighting function better go to 0% or 0 at the other handles. So these weighting functions should start at 1 and smoothly fall off to 0 at the other handles. For point handles, this is clear. For bone handles of a skeleton, the weight should be 1 along the entire length of the bone and 0 along the entire length of all the other bones. And then for barycentric coordinates, or for cages, we have the same situation as points, so the vertices are really point handles, but we have an extra condition that the weights vary linearly along the length of the cage faces. So faces are edges in 2D, but they're going to be the facets of the cage in 3D. So we just say, okay, they need to be smooth, they need to go from 1 to 0, they need to sort of diminish as you get farther away from the shape. It seems like we could come up with some easy techniques to figure this out. So in particular, you could say, just take inverse distance with respect to the point and normalize that and call that your weighting function. But we need to be careful here because if we use distance measured in the Euclidean space, sort of the entire embedded space, just R2, the entire plane here, we can get problems where the points or handles that are semantically very far away from a part of the shape are still implying influence. So as you can see here, the handle in the bottom lip is sort of pulling on the top lip, and the handle on the top of the head is pulling up on the bottom lip there. So we have a very unintuitive response. We'd expect that the response of that top handle on the clam to sort of go around, and its influence to sort of spread through the shape. And in this way, we'll say that weighting functions that do this, they are somehow shape-aware. They're measuring distances intrinsically in the shape with respect to geodesic distance rather than with respect to Euclidean distance. One way to capture shape awareness is to embed the shape in a cage and work with generalized barycentric coordinates. So we are all familiar with barycentric coordinates in a triangle, right? The barycentric coordinates in the triangle are just the linear functions that goes from 0 on one edge to 1 on the other vertex. And why do we call them coordinates? Is because any point inside of that triangle we can represent in terms of a weighted combination of the endpoints where the weights are the barycentric coordinates. So it gives us a representative, instead of using x, y to store the point of some part of this gingerbread guy, we can represent him as a weighted combination of the rest positions of the vertices. So this naturally leads to a deformation method where we say, okay, we now know how to represent all the points on the interior in the rest pose. If we start moving the vertices, we'll get a deformed version of those points. And you can show, so this here you're seeing that the deformed version of the vertex is a weighted combination of the deformed version of the control cage. So in some sense, this is a simpler direct skinning method than linear blend skinning. We don't have transformations of the control points. We're simply just blending the points themselves. But we have this extra condition that the weighting functions are coordinates. They're coordinates in the sense that they reproduce all the rest vertices. And we can actually see that this simple method of generalized barycentric coordinates is a special case of linear blend skinning, where we restrict all the transformation matrices to be translations. And I'll show that very simply here. So if we have a translation matrix, we know we can split that into two parts. The linear part, or the rotation part, must be an identity matrix. And the translation, well, it should take each cage vertex from its old position to its new position, C prime here. So we can get rid of that identity part. And we can see that if we apply our coordinate assumption on the weights, that we can get rid of the difference between the blended, so we see here we have the blend applied to the original cage vertices, which we know equals V, so these two cancel out each other, and we simply get a weighted blend of the deformed cage vertices. So in this sense, the generalized barycentric coordinates deformation are a special case of linear blend skinning. And we can understand higher order generalized barycentric coordinates as sort of a rediscovery of linear blend skinning in the context of cage-based deformations. So generalized barycentric coordinates is a wide topic in the literature, and there are all sorts of methods for coming up with these kind of weighting functions, these barycentric coordinates automatically, and they're not created equally. It's interesting to sort of enumerate all the sort of properties that you have in the single triangle case and see how many of those properties can you get in the general polygon case. So if we're just considering barycentric coordinates for a triangle, we have some interesting things. They're just simple linear ramps, but we can enumerate nice things about them. So all of the coordinates are between 0 and 1. We have no local extrema in the coordinates. They're smooth. They're one at one control point and 0 at all the other control points. And sort of the game of generalized barycentric coordinates is to come up with a new coordinate scheme that works not just for triangles, but also quadrilaterals and pentagons and so on, that fulfills as many of these properties as possible. And so far to date, you can see, I don't expect you to really parse this entire thing, but the important part is that not all of these properties are actually being satisfied by any particular group. So in particular, it seems that the positivity requirement, that the coordinate functions are between 0 and 1, really seems at odds with the property that the, what am I trying to say here? Close. I have to reparse that. So the positivity requirement, that the weights are between 0 and 1, if we look in between these two columns, it really seems at odds with weighting functions that are defined via closed form expression. Meaning you can just use the sort of combinatorics and the positioning of the cage vertex, and you can immediately spit out what the weighting function is at any given point. We don't have to rely on any sort of numerical optimization to figure out what the weighting functions are. So it's interesting to then ask, as an open problem, is there no free lunch here? Can we write down some sort of theorem that says that some of these properties are mutually exclusive, that you can only have so many of these properties and not all of them? In any case, I'll argue to you that working only with cages, and in general, generalized barycentric coordinates are only defined for cages, is somehow too restrictive to the user. So if I ask the user to open up the jaws of this piranha character, but you have to use an exterior cage, this would be really annoying. Because I'd have to leave the cage all the way through all of its teeth if I want them to separate. And not only is constructing the cage annoying, now to deform it, I have to move all of those cage vertices. And you can almost imagine I really need a separate deformation scheme just to move the cage vertices so then I can apply a deformation on the character. When instead, if we relied on a linear blend skinning deformation that was controlled by bones, this could be really easily controlled by just 3 bones controlling the jaw, as is natural for this kind of character. So if we want to work with interior skeletons, we can ask what would be sort of the equivalent way of getting these nice properties, smoothness, and that the weights fall off with respect to distance measured inside of the shape for skeletons. And one interesting method, and I'll present an alternative view of this method than it was presented in the paper. So you can sort of go home as homework and try to understand this view in comparison to the way it was presented in the original paper, Baron and Popovich, is to see each bone as being rigidly attached to the surface, or see each point on the surface as it can only be, its weights have to be 100% to one bone and 0% to all the other bones. So just attach every vertex rigidly to one of the bones. And this will lead to a terrible deformation because we know these weighting functions aren't smooth. But then we can set up an optimization problem that smooths these weights over the surface. So we see that Dirichlet energy popping up again in here. This is an energy that's defined with respect to the metric of the surface. So we're saying, find these smooth weights that are as close as possible to these rigid weights controlled by some weighting factor. And if we do this, we can understand these weights as being a blended version of a rigid attachment to the bones. So we have a smoothness term and a data term here. So a very sort of classic data smoothing problem. We have a noisy input function, and we just like to smooth it over the domain. This second order smoothness term will turn out to be a problem if we want the control handles to lie directly on top of our shape. As is wont if we have point handles. So point handles, it's very natural to just pluck them down and place them directly on the shape that we're controlling, especially in 2D. But if we rely on a second order smoothness term, then we get nasty discontinuities happening at the control points themselves, because we're requiring that the weights are 1 there and all other weights are 0. So we have a hard constraint on the value of the weights at those point handles, but we only have a second order energy. And you can show that there's not enough expressiveness in the solutions to these type of energies to capture smoothness at these control handles. But you can get this kind of smoothness if you increase the order of the derivatives that you're looking at on the shape. So with this, you can get nice smoothness across the point handle. So we see that the texture is not being torn across that point. Solutions to the energy optimization that you see under each of these correspond to nice smooth PDEs. So on the right-hand case is the famous Laplace equation that corresponds to solutions of the Dirichlet energy. And on the right, we have sort of a bi-Laplace equation. The Laplace of the weighting function should be 0. So as we saw, we sort of have problems and we restrict ourselves to only one of these type of control handles. We had issues if we only had pages. If we have bones, but we require them to be inside, we can't work with point handles. And this whole circle, this picture sort of completes itself. There are cases where it's really nice to have a cage. If we wanted to scale this vacuum character, it's nice if we can place a cage so that the bar of the vacuum stays perfectly rigid and we can apply some sort of nice, interesting scaling effects to the vacuum here. And the goal of a series of works that colleagues and I did in the last couple of years have been focusing on combining all of these handle types into a single framework of optimization. So we can compute weighting functions that, can you see this? Good. I think I know why the computer is dying. So I can use a rigid collection of bones, a little skeleton to control the jaw of this alligator. I can use a cage if I want to apply some effects on the belly. And I can add some points that'll be nice for making a flexible region of the tail. And now our method is computing weighting functions over the entire surface. Oops. That we can now see here. So here's the weighting function for this bone, for the next bone, for that bone. You can see it for the cage vertices. We see that this cage vertex is being blocked by the cage here, so its influence is contained inside of this cage. Yeah, now I can apply a nice little deformation to this guy, make it look like he ate something. So points are really nice if you have rotation, so you can easily get some flexibility in that tail. So here you get a little animation of that alligator. So I'm going to, I think I'm going to hop over a few slides here to jump to sort of the punchline. Which is here. So again, this is one of these tables where you want to see that previous methods, in some sense, aren't satisfying all the properties that we'd like to have. And we sort of try to adapt them to deal with all types of handles for points, for skeletons, or for cages. We either don't get the smoothness that we want, or if we jump quickly to higher order PDs to define our weighting functions, we lose other properties, like the weights suddenly become non-negative and are highly oscillating over the domain. And I dangerously wrote here that you can get a free lunch, which of course there's probably some missing criteria here that we're not considering. But in the series of works that follow, we showed that through an energy minimization that starts with this higher order energy and a series of constraints, we can actually add up all the properties that we enumerated before and get a nice set of weighting functions. And those are the weights that I showed you in the last case of the alligator. And these weighting functions extend nicely also into 3D. So in 3 dimensions, if we have a triangle mesh representing our shape, like this armadillo here, we can tetrahedralize the interior of the shape and solve for these weighting functions over that volume. So here's a skeleton inside of the shape, and we have some point handles selected on the surface. And here are a few weighting functions. We see nice fall off from that point handle, and then we can cycle the weights on the skeleton. So I think in this case it's really important to point out that creating weights that achieve this kind of smoothness effect automatically is really dramatic if you compare to the amount of hours that it would take a traditional artist to sit and paint these kind of weights. So within a matter of minutes, a novice like myself can create a somewhat interesting deformation of an armadillo. It's like pull its ears up. Maybe like rotate its tail. No, So that the painful process of creating the weights is now gone. And the one thing that I'll say is that as you saw me sort of struggling through the transformations, painting the weights is not the only problem. So to make this character really like come alive and feel like he's full of life and moving around, I really had to go and touch every bone of the skeleton. And even then, I really, at best, created a single good pose. If I want to make a character come alive quickly, what I'd like to do is just specify a few constraints on where the transformations go and have the rest of them computed automatically by the computer. Maybe then later I can go and fine-tune them. So this leads to a method where you see here, I'm just controlling the yellow points of this skeleton, and those transformation matrices are being computed automatically by an optimization that's chugging away as I'm controlling the shape. So here the weights have been pre-computed, and now also the transformations of most of the bones are being computed automatically, and only these constraints are being satisfied. And I can change these constraints at runtime. So I can say, okay, now the head is free to move around. I can say, okay, now the head is like fully pinned down, so I can even control its rotation, I think. Yeah, there we go. And you'll notice something interesting about this skeleton. I've purposely disconnected the top half of the skeleton to the bottom half of the skeleton. And this is interesting if you're familiar with inverse kinematics, that we typically control end effectors by measuring some sort of cost function through the skeleton. You can view this work as an inverse kinematics that's somehow shape aware. It's measuring the cost of choosing the new transformations insofar as they produce the best possible deformation. So changes that I applied to the top half of the skeleton will propagate through the shape to the bottom half. So as he bends, his knees will actually bend here. And lastly, I want to leave you with what I think is really the exciting direction to look at for how you as researchers might want to exploit linear blend skinning, is to see linear blend skinning as a coherent subspace of deformation. If we consider a triangle mesh and the entire space of deformations, and we just pluck a random deformation from this space, we'll get something like this. This is just a random deformation of the mesh, and it's complete garbage. If instead we consider the subspace of mesh deformations spanned by a linear blend skinning rig, and we pluck out a random deformation, we might get something like this, which is actually now entirely plausible. This does look like a deformation of a character that could actually do that. So in this sense, we're inheriting semantic information from the skinning rig that's not embedded purely in the geometry. In contrast, we saw that POW before. If we only look at the surface geometry of the character and nothing else, we can at best sort of come up with these like rigid eigenmodes, which are loosely related to semantics, but they don't capture things like bending directly at the elbow. So we're inheriting semantics from the rig. And the regularity of working in this subspace allows us to do really interesting things. So in this example, we're automatically optimizing the deformations of 100 of these armadillo characters in real time. And by working within the linear blend skinning framework, the actual deformation of all these characters is done on the GPU. We're still using linear blend skinning, so we're still taking advantage of those GPU shaders that are moving the vertices just in time before they need to be rendered on screen. So I'll leave you with a few open research questions that I think would be interesting to tackle. So I mentioned the implicit skinning work that some of our colleagues in France have been working on. But I think in general for this problem of posing and helping the user choose transformations of a character in real time, dealing with contacts is still an open question. The possibilities that are out there are still not reaching the same frame rates that are competing with the actual rendering of the character. And lastly, we're seeing like major strides in how leveraging the immense amount of data for images and video are enabling image processing and video processing, I think the same sort of technique can be leveraged or at least altered to be taken advantage of in this case. We can develop even more semantics, and how can we get those semantics before we create these rigs? And finally, it would be interesting to consider better interfaces for controlling these characters. So far I've been controlling all these characters just using the cursor and the keyboard, but you could think of what is exactly the right deformation interface for controlling a real-time character. So hopefully I've given you a glimpse into how recent research can automate each of the steps of this very labor-intensive process of constructing the handle set, computing the weights, and finally choosing the transformations to control a linear blend skinning rig. And I'll leave you with that. I guess I will, yeah, I would like to thank my, my advisors, my co-authors, collaborators, and funders. And finally, please check out our online resources. So the skinning.org website contains all the course notes, slides, and especially the slides and course notes for the other parts that I didn't cover. And then for a lot of the things that I talked about today, you can find C++ code and demos in the libigl GitHub repository. And also, if you're more of a MATLAB person, you can play around with the geometry processing toolbox, which contains many of these techniques. And with that, thank you for your attention.